Hey, good morning, Calculus 2. Let's do a couple more shell method problems. We're in section 7.3, learning how to do the volume with a new method called the shell method. So it's still a solid of revolution. I got a couple examples I'll get to, but let me point out the formulas are these again. When I wrote down these formulas in that last video, I called this R of X. It was the radius to the shell. Your book uses the Greek letter rho here. Looks like a P, but that's the Greek letter rho for radius. So that's the radius to the shell and the height of the shell. That's good language that's what you're looking for. The radius to the shell and the height of the shell. And like I said, I called that R of X instead of rho of X. That's okay. So if you're going around a vertical axis, it's opposite from the disk method. You're working in X's. When you go around a horizontal axis, you're working in Y's. So it's a different geometry. It's a different way of thinking. Let's try this example. Now, one of the hard parts, I think, is if you read this, you gotta sketch the picture. So a graphing calculator sure helps, or some kind of graphing somewhere, some kind of graphing website or something. So I'm going to help sketch this real quick. I kind of know some of these shapes. I'm going to move over here. I'm going to sketch this picture, and then I'll save some room to work there. This is an upside down parabola, and I think it hits the x-axis at 4. And it continues. But it's this upside down parabola. If I factored out an x, I would find out it has these x-intercepts at 0 and 4. So this is the region. This is the region. It's bounded by the parabola, and it's bounded by y equals 0, which is the x-axis. So that's the region. And it's being revolved around the line x equals 6, which is kind of interesting. Hang on, that's over here. The line x equals 6 is a vertical line. So we're revolving it around the line x equals 6. So there it is. It's a solid of revolution. It's kind of weird. I don't know what the hell you would call it. Half of a inflated donut. I don't know. It's kind of a funny shape. Half of an inflated donut, I'll call it. Anyway, there's a bunch of volume of this shape going around here. So we want to find the volume. So we want to do the shell method, I swear. I don't want to do the disk method. The disk method, I don't want to talk both methods, although it's fun to talk strategy and try to teach you how to think through your strategy. But the disk method would be in Y's. The disk method would have a hole in it. I don't want to do that. I think that's tougher than the shell method. I think is fairly easy. The shell method, step 1 of the shell method is draw an arbitrary shell. So here's an arbitrary shell, parallel to the axis of revolution. So you draw an arbitrary shell parallel to the axis of revolution, and then you need 2 things. You need the radius to the shell and the height of the shell. The radius to the shell is that distance. Last time I did an example where the radius was from the y-axis over. That distance was x. This distance is not x. If that distance is x and this is 6, can you tell me that distance? Thank you very much. That's 6 minus x. The radius to the shell is 6 minus x in this example. The height of the shell, please. The height of the shell is very obvious. The height of the shell is the function. The function is that 4x minus x squared. Awesome. That's the hard, that's it. That's the hard, that's not it. You got to set up an integral and do it. But you had to identify, draw the picture and identify that, I think, is the hard part. That's the difficult part. The rest of this is an integral. I'm going to call it the volume. It's going to have a 2 pi in front, and I'm integrating the radius times the height. The radius is 6 minus x this time. The height is the function. I'm going to do this with respect to x, and I need some bounds. So this shell, to get that volume, this shell has to move throughout this region. Notice it doesn't, this shape does have a hell of a hole in it, but the shell method doesn't worry about the hole. because we're not going to let that shell go into that hole, because we're going to set up bounds that go from 0 to 4. We're never going to take the shell into the hole to get the volume we don't want. So we don't have to subtract it out. So the shell moves from 0 to 4, and that gets the volume we want, from 0 to 4. Even though I'm spinning around 6, I'm not going in there. So, I tell you what, I like problems that just say set up the integration. Of course, you want to do it to find the volume, and I'm also sort of teaching you that, but the truth is, I think you can FOIL this out. I don't have to teach you how to FOIL. After you FOIL it out, it's a polynomial that you can integrate. I think you can integrate each term of the polynomial. Then you have to evaluate it from 0 to 4 with a 2 pi and simplify it. Anyway, you can do that. I can help you, but you can do that. I'm going to move to example 2. So I like these problems that say set up. In fact, sometimes my test questions are set up the integration, and then you don't really have to do it. Some of them. A lot of them you have to do some, of course. But sometimes it's set up the integration, because that's the skill I'm trying to teach you. All right, let's do this example. Example 2. Again, the trick is coming up with the picture. I'm going to move over here. Maybe I'll have a little room to set up this picture. Sorry. That's the x-axis, the y-axis. And here I go. Y equals x cubed, of course. I know how to draw y equals x cubed. That might be a little exaggerated, but that's y equals x cubed. X equals 0. Be careful. Some students make a mistake. X equals 0 is this y-axis. So x equals 0 is a boundary. This y equals x cubed is a boundary. This is part of the problem above. I think I'll just get rid of that. Problem above. And then I have, what else do I have? X equals 0, y. Oh, y equals 8. Y equals 8 is this horizontal line. It's supposed to be horizontal. Horizontal line, y equals 8. Hey, when y does equal 8, can you tell me what x is? When y equals 8, can you tell me what x is? I'm not sure if I need it, but when y equals 8, x is 2. So wait a minute. Y equals 8, y equals x cubed, and x equals 0. So this is the region. Be careful. Sometimes people sketch the wrong region. That's not the region. This is the region. Y equals 8, x equals 0, y equals x cubed are the boundaries. And then I'm going to take that region and spin it around the x-axis. Okay, spin it around the x-axis. All right, I can do that. We can do that. Because it's around the x-axis, I'm tempted to go back to, I'm thinking about the dis method. I like the dis method around the x-axis. You get to work in x's with the dis method. This one does have a hole in it, means I have to subtract out the inner volume with the dis method. Anyway, I'm going to force us to do the shell method here. There are some problems where you get a choice. Pick the dis method, pick the shell method. There are some problems where we're trying to force you to learn these methods, so we force you to do the dis method, force you to do the shell method. So let's do this with the shell method. And what's new about this is it's a shell method around a horizontal axis, and I haven't done one of those, so I will be working in y's. Remember step 1 of the shell method, draw a representative shell parallel to the axis of revolution. Okay, that's this. A representative shell parallel to the axis of revolution. This is the axis of revolution. All right, then I need 2 things. I'll do it over here. I need the radius to the shell. Oh, and it's going to be in y's. How do I know it's going to be in y's? I can memorize the shell method around a horizontal axis is in y's. I can just memorize that. Or I could, when I drew this shell, what's the thickness of the shell? It's dy. This one was dx. The thickness of the shell was dy, so that tells me I'm working in y's. Anyway, I need the radius to the shell. It's this distance from the x-axis up to some arbitrary place. It could be here, 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 it could be here. it's just it's not the function. I'm not hitting the function. I'm hitting this shell that's arbitrarily anywhere in there. We call that distance y. I called that distance x. I called that 6 minus x in the previous problem. I don't want to confuse you. I'm sorry. That distance is y. The radius to the shell is y. What about the height of the shell? I need the height of the shell. Well, there it is. And when it's sideways, you might want to think of it as the length of the shell, but it's the height of the shell, and it's just that distance. It's the function. But it's the function needs to be, it's x written in terms of y. It's the function in y's. So not the function y equals x cubed, but if I solve for x in terms of y, it would be y to the 1/3 or the cube root of y. I think that's the height of the shell. It's the function solved for x in terms of y. Y to the 1/3. Dude, that's it. I think again, I say, dude, that's it. I mean, that's the hard part. Drawing the picture, drawing your shell, and figuring out the radius to the shell and the height of the shell. Then you set up your integral. I can set up an integral for this. It's going to have a 2 pi in front. It's going to have the radius to the shell, the height of the shell, the thickness of the shell. That's it. Oh, I need some bounds. I need some bounds. That shell's going to move. Well, that shell's going to move all throughout this region. I think it's going to move from y equals 0 to y equals 8. I am in y's. The bounds are in y's. I think it goes from 0 to 8. And we've set this up. If the question said, please set up the integral, we're done. We set up the integral to get the volume. If the question wants the volume, then you got to do the integral. Let's just do this one real quick for fun. I'm moving up here where I can do it. You know, that's y to the 4/3. That's y to the 4/3. If you do the integration, I think you get y to the 7/3 times 3/7. Did I do that right? I think I did that right. That's y to the 4/3. Add 1 to it. That's adding 3/3 to it. So you get y to the 7/3. Divide by 7/3, which is 3/7. There's a 2 pi out in front of that. And we're going to try to evaluate from 0 to 8. Okay, so I did a couple steps in my head, but I talked you through it. There we are. This is easy. You plug in an 8. You know, when you plug in an 8, you have 8 to the 7/3. And that seems weird, but hang on, I'll talk you through that. That's a cube root. It's a cube root of 8 raised to the 7th. The cube root of 8 is 2. Raise it to the 7th, and it's 128. So I have 2 pi times that 3/7 times 128. Is that what I'm saying? That is what I'm saying. The cube root of 8 is 2. 2 to the 7th is 128. Well, all right. Well, good luck with that. That's 256 times 3, 768. You kidding me? 768 pi divided by 7. Not sure I did that right. Not sure I did that right, but I'm kind of confident. That's the volume of this shape spun around the x-axis. That's kind of a weird shape. All right, thank you guys. Good luck. Try some homework.